So the big thing about these is recognizing that for every line, we need a direction vector and a point. And so your goal is to always come up with that direction vector or point. In this case, I'm giving you 2 points, so you've got that part satisfied. How do I find a direction vector, though, between the 2 points?
You subtract.
Yeah. So the D, let's choose a different color than that. D, in this case, then we're just going to subtract the X's, the Y's, and the Z's. So be 1, 6, and -6. That look right?
Yep.
Yeah. And then the, oh, hi, Brenna. You in a car? You're muted.
Brenna, you're muted.
I'm just on my break at work, so yeah.
Aren't you cool?
Yeah.
That's what I like to do on my break, is come in and listen to a math lesson.
Yeah. I gotta go to my math lesson. I'll be back.
That's awesome. Okay, well, we'll keep going then. So we're saying that for every line you need a point and a direction vector. So in this case, we found the direction vector by subtracting the points. So 3 minus 2 is 1, 6 minus 0 is 6, and -1 minus 5 is -6. And then it's a matter of just remembering which is which for all the different versions of the lines. So the vector 1 is the case where we take X minus the point. So it's kind of like the roots of quadratics. So X minus 2 would be the point that would get us there. Y minus 0, you wouldn't have to write the 0. And Z minus 5, given that I use that point. Of course, you could have used this point and that would have been right as well. Equals, and then some constant or some scalar multiple. So I chose K, and then the direction vector. Any questions for that?
Yeah. When you found the direction vector and you did the subtraction, does it matter which point you subtract from which one?
No, that's a great point. Because it's a line, and a line can have direction, be described by direction vectors going this way or this way. So both would be equally correct.
Okay.
Yeah, so you could very well have said K -1, 6, or sorry, -6, +12, right? And actually any scalar multiple of that would also be legit. So if you wanted to double it and have like 2, 12, -12, that would also describe the same line, because as long as you've got a point in any direction vector, so if I, had this direction vector is that long, or a t that was smaller or larger, it would all describe the same line. So good question. Okay. And then the one that's a little bit odd, and I had a few emails about, was the symmetric one. So the symmetric, you take all of these direction vectors and you divide it and say they would all be equal to K. So the X minus 2 would get divided by the X component, which I'll just use this one, is 1. The Y minus 0, I'm going to leave the minus 0 in there, although you don't need it, would be divided by 6. And then the Z minus 5 is divided by -6. So in this case, this is a useful version of the symmetric equation of a line, because you can get the point easily and the direction vector easily. But the proper version doesn't allow for negatives on the bottom. And so we have to adjust this as a proper answer by taking this negative and putting it to the top. And when it goes to the top, it goes with both. So the Z becomes negative, and the -5 becomes positive over 6. Okay, so we're moving that negative to the top. Of course, you can leave it like that, but what happens most often is we like to put the 5 out front, and this then becomes 5 minus Z over a +6. Okay, so this is what I've been saying is the proper version. No negatives allowed on the bottom, but it's not the useful version because it doesn't clearly show what the direction vector is. The rest are fine because there's no negatives, and you can even you don't even need to write the 1 over 1 for that version. But you see, this is not the direction vector, right? When it's in this version, because it must have in order for it to be useful, you have to have the letter first, and it'd be z minus 5. Okay, so it's kind of confusing. This is the proper version, but if you actually want to get information from it, you need to convert it to this, where you can actually get the proper or the correct information. Okay. So that I wanted to do that one because I knew this. It's kind of snaky with the symmetric version, so we can have that conversation. Next, so how does this one? This is then getting information from it. Do you want me to do this one, or are we okay with this one, or what do you think?
Do you want to show us the answer and then we can compare?
Yeah, sure. So actually, by the time I write down the answer, I could pretty much show all the steps. The big thing is, again, we need a point and a direction vector. This one's already got a point, and so we just need the direction vector from this guy. But you see right here that it's not in the useful form because the z is negative, and it's written second. So we have to convert this this symmetric version of the line into the useful version. So x minus 2 over 5 is okay, and y minus 4 over 3 is okay, but this one is not. So the z can't be negative when you're trying to determine the information, which means you need it to be positive, and it's like moving that negative from the top to the bottom. So the shortcut is everything changes signs. The 1 becomes negative, the z becomes positive. So on the top, it would be z minus 1. And the bottom would now become negative. So that step that I kind of skipped is this, -1 plus z over -2. So taking the negative from the top and putting it on the bottom, and then just rearranging the order of that. So then this allows this direction vector to be read properly. The direction vector is 5, 3, -2. That make sense?
Yep.
Okay. And then there's our point. And so now we got to write it in parametric. So parametric is, I think of the pairs of things, even though there's 3 of them. So it describes what the x does, the y does, and the z does. So the x then is x equal to the point, the x coordinate. So 2 plus a scalar multiple of the direction vector. So that would be 5k. The y would be the -7 plus a scalar multiple of the direction vector. And z would be the 1, and it would be plus a scalar multiple of this, but because it's a negative, it'll be plus -2k, so we would just write it like that. Okay, and I could have used t, I could have used anything else, but all of that would be the same. Good? Okay.
Yep.
All right, so number 5, C. We're just, I think we might as well just keep going with this. It seems to be going okay. So scalar equations is one that we're going to be using quite a bit. And so it's best if we just talk about this one. So develop a scalar equation for a line given this information. So first off, we got to get information from this. It doesn't look like it, but it is in actual parametric form. I'm just going to write it underneath so you can really see the parametric form. So there it is, the parametric form. And from that, you can get the 2 bits of information you need. You need the point and a direction vector. So what is the point from this line that I put in the box?
1.
Sorry, the whole coordinate point.
2, 1.
Yes. So the x part is 2 and the y part is 1. Good. And then the direction vector.
1, -3.
Yep. Okay. And sorry. So that's helpful information. And if we were finding the vector, the general, the symmetric, the parametric version of the line, this would all we would need. But the scalar, there's one little other trick. The scalar equation, the coefficients on the scalar are the normal to this line. So the normal is one that's perpendicular to this line. So if our direction vector is that way, so you can imagine like we would have, this is what our line might look like. And so we have our direction vector that might be described that. It could be a longer version or it could be in the other direction, but all of those describe that. The normal is a line that is perpendicular to this. And since we are in 2 space, that's the only possible, well, not the only one, but it can't come out of the screen. Okay, we're only in 2 space in this example. And so that's why we can describe a normal. It could be that normal, it could be a longer one, and it could, of course, be going this way and still be perpendicular. And it could exist anywhere on that line. They all work. But it turns out the normal is the coefficients of the scalar equation. So what we need to use is our little shortcut from last unit to describe something that's perpendicular. So what is perpendicular to 1, -3?
3, 1.
Yes. So Tara decided to switch them, which of course you have to switch them, but she decided to make the -3 negative. So negative of a negative made it positive. Someone else could have said -3, -1, but that kind of looks more difficult. And you could have done a scalar multiple of this as well. -6, -2 would also been a correct answer. But this is the most common and obvious one. So now that we have our normal, because we learned that the coefficients, are the normal is the coefficients of the scalar equation, we can go 3x plus 1y plus something is equal to 0. And to get that something, you're going to take the point and sub in the point. So the point in here is 2, so we're going to plug in the 2, and the y is 1 plus c equals 0. 3 times 2 is 6. Plus 1 plus c equals 0. So that's 6 plus 1 is 7. Bring it to the other side is -7. And so therefore the equation is 3x plus 1y minus 7 equals 0. You're muted there, Brenna.
I have to go now. Is that okay?
Absolutely. That was nice of you to come by.
I'll watch the recording. Are you going to post it again?
Yes, I will.
Cool.
Especially the part with you in the car.
Okay, yeah, the best part.
The best part, exactly.
Yeah.
All right, well, thanks for stopping in.
Thank you.
Bye. That was awesome. So any questions about number 5 there?
I kind of got lost on it. Where is the numbers out front of the x and the y? Where? Oh, wait. No, never mind. I found it.
Right there?
Yeah.
Yep. Yeah. So once we know the normal, then the normal can go out in front as the coefficients.
Okay.
Okay. And that'll be
Yep.
helpful when we move into Unit 9 as well. Yeah. And then the point came from right here. And then you just sub in the x and y values to get your c constant at the end.
All right.
Okay, great. Good question. All right, let's keep going. This one I'm going to do really quickly. I realized afterwards that on the video I showed one way to answer this question, and there is a second way to answer this question, so that some people seem to like better. So I'll do it the second way, and you can decide which you like better. So in order to determine whether these describe the same line, it's not obvious whether these are the same line, because if you think about it, you could use an infinite amount of points to describe this line, and you can use an infinite amount of direction vectors. So often you might get a different point and a different direction vector, and it's hard to tell if those points are on the same line and if the direction vectors are the same. So one thing you can do is definitely investigate the direction vector, and it will tell you if they're not the same really quickly. So that's what we'll do with each of these. So we'll look at here, and I'll describe D1 as the direction vector for line 1, and it's right there. So 3, -4. And D2, well, again, here comes that annoying version of the symmetric equation, because you see the y is a negative, and it can't be. So in order for it to be useful, we're going to do that little trick, make everything negative. So the 2 becomes negative, the y becomes positive, and it's y minus 2 over -4. So that allows me to see that the direction vector is 3, -4. Oh, that's direction vector 2. So far, so good?
Yep.
Okay. So right away, you see that these two direction vectors are parallel because they are, well, they're the same. Even if this one had been 6, -8, they still would be parallel because one is a scalar multiple of the other. So it would just be saying that the direction vector, the first one is only this long, and the second one is twice as long, but it's still in the same direction and still describes the same line. Okay, but it turned out these are bang on exactly the same. And so we know right away that they are parallel. Now, that doesn't guarantee that they're the same line, though. So I heard I had lots of positive feedbacks from all my demos with my pencils and my day 9 or my unit 9 video. So I'm going to use my pencils again. I've been doing it all week, making other videos. It's been rather entertaining watching myself try and do this. Okay, so here's one line, and here's another line. These two lines are parallel because they're scalar multiples of each other. The direction vectors are, but they're not necessarily the same line. These are the same line and also have the same characteristics. Direction vectors are scalar multiples of each other. So the question is, how can we tell the difference? And that is where we go off and decide if they're distinct. So distinct meaning their own separate line. So I think the way that I did it before in the video is we took a point from one point and drew it on the other, or sorry, we took one point from one line and saw if it existed on the other line. So if you want to try that method, you can, but I'm going to show you another way that you might like better. So in the other way, we're going to need a point from line 1. So I'm going to call this P1, and it's relatively easy to see that the point is 8, 1. Remember, opposite to what you see in there. If it's x minus 8, that means the point must be 8. Y minus 1, the point must be 1. And then I'm going to take a point from line 2 and call it point 2. And again, I can look at the top and see that the point is 1, 2. So what I'm going to do, and this is a little bit easier, is to find the direction vector between these two. Okay, these 2 points. I'm going to call it D star. So before I actually do that, let's try and visualize what I'm doing. Let's assume they're different. Okay, so they're parallel and different. So I'm going to take a point from this guy and a point from this guy. And I'm going to find the direction vector between them. So I'm going to take this point and try and find this direction vector here. Okay, if they are separate, like I'm holding up here, and I've got the direction vector, and I take the direction vector, this steel direction vector, this one that I have here, will not be a scalar multiple of these guys, right? So that would suggest that they're different. If they were the same, and I took a point from the blue one and a point from the yellow one, and found the direction vector of those two, they would be a scalar multiple if they are the same line. Does that make sense?
Yeah. Makes sense to
Okay.
me.
So I've taken these 2 points and I want to find the direction vector between them. So I'm going to subtract them. I'll do the second one minus the first. So that'd be 1 minus 8 is -7 and 2 minus 1 is 1. And this D star is not a scalar multiple of our other direction vectors. So that means that it must be 2 separate lines, okay? Because the point from this guy to the point from this guy produced a vector that is different than the lines themselves. Had they been the same line, any 2 points you take on these lines would be a scalar multiple of the original direction vectors. So that means that these are not the same line. They are parallel, but they're not the same line. And the word we use to say that is they are distinct. Does that help?
Yes.
Okay. All right. Last question. Is it last question? Yeah. So, and then really all of this leads up to the last question about finding the intersection of them. And this is where the math starts to kick in a lot. So you're going to try and investigate whether these 2 lines intersect. So we're going to assume that they do. That'll be the first thing, okay? But even before we assume they do, we should make sure that they're not parallel. Because if they're parallel, you don't need to do all of the math that follows. If they're parallel, they're either distinct like this, and there's no intersection, or they are parallel and the same, and therefore they intersect infinitely. So before you even do anything else, check to make sure that they are not parallel. So I'm going to do that really quickly. What color am I here? So D1, just from reading it off, is 3, 5, 4. And D2 is -1, 2, -3. And the book tries to mess you up by changing the order of this guy and the order of this guy. So you got to make sure you pick them off from the coefficients. And hopefully I did that correctly.
Yeah, that was same.
Yeah. Okay. All right. Are they scalar multiples of each other?
No.
No. Okay. So even if one, they're not the same, but even if one was twice as big or a third as big or whatever, they would be parallel, but these ones are not, so they're not parallel. That means if you've got 2 lines and they're not parallel, technically they should touch. We discovered there's a special case where they don't, but we're going to assume that they do. And when they touch, their x coordinates and their y coordinates and their z coordinates would be exactly the same. It's the only spot where the x and y and z for this guy are the same as the x, y, and z for this guy. So that's the point of intersection. So by saying that, we're going to assume they intersect, and each component, the x components are equal, the y components are equal, and the z components are equal, only at that spot. So we would write 1 plus 3s equals -t, 5s equals 2t minus 9, and 4s minus 3 equals -1 minus 3t. Make sure I've written that down correctly. The most common mistake I see, and I do it even, is just writing it down or getting a sign backwards, not necessarily the math itself. Okay, so that's when they're equal to each other. So now we're going to rearrange this so it looks like a grade 10 question. So I'm going to put the 3s, I'm going to leave it there. I'll bring the -t across and make it +t, and I'll put the -1 on the other side and call that equation 1. And then I'll have 5s minus 2t equals -9. I'll call that equation 2. And 4s plus 3t equals 2, and I'll call that equation 3. Any questions so far? All right. So did we remember this stuff from grade 10, or did you have to shake your brain a bit to remember this?
Once you started doing it, it slowly came back.
Yes. So the key in this is that we have two unknowns, S and T, and all we need to solve two unknowns is two equations. If you think back to grade 9, when you had like 2x plus 1 equals 9, there's only one unknown, and I only need one equation. I can work backwards on this to figure out that x equals 4. But when you have two equations, you need when you have two unknowns, you need two equations to be able to do that. And if you had three unknowns, you'd need three equations, and that's coming up next unit. But here, I've got three equations. So I only need two of them. So I'm going to ignore one of them and only solve with two. But it does have to work for all three. So who would like to, what do you recommend I get rid of? Which variable do you recommend I get rid of, and from which equations?
You can multiply the first one by 2 and then get rid of the t's.
Excellent. With the second one, right?
Yeah.
Yeah. So I'll do this over here because I run out of room underneath. So multiplying the first one by 2 makes this 6s plus 2t equals -2. And I like to renumber these. You don't have to, but I do. The first one I don't do, or the second one I don't do anything to it. So 5s minus 2t equals -9. I do renumber it. It's not necessary, but I do. And then you're right. You're going to add those. 4 plus 5 makes this the 6s plus 11. Oh, excuse me. 6s plus 5s is 11s. The t's do eliminate, which is the whole point of me doing it. And this is -11, and s equals -1. This sounds familiar. Is this the same one that I did in the video? I hope not.
I don't think so. I can check.
I remember it was 11 and 11s.
Yeah.
And -11. Yeah. I'm not sure if it's the same question.
Right. Okay. Well, let's not panic about it. All right. So we've got our S value. Now we need to figure out our T. So this is going to be really messy on the screen here, and I apologize, but we're going to take T and sub it into either the first one or the second one. We've ignored 3, so make sure you don't sub it into 3. So might as well sub it into the first one. So sub S equals -1 into number 1. So this will be 3 times -1 plus T equals -1. I'm going to try and save some written steps here. 3 times -1 is -3. Bring that across is +3. So T equals 2. Hope I did that one okay.
Yep.
Okay. Any questions to this point? Okay. So I'm going to now move over to a new page because I'm just running out of room here. So but I'll come back here. So I've got a value for S and I've got a value for T. These are not points, right? They're not an X, they're not a Y. They're just the scalar multiples necessary to get the appropriate points. I could take these and sub it in and get possible points, but I have ignored the third equation to do this. And it has to satisfy all 3. You can imagine that since we only used the first 2, technically we only found where X and Y are equal. There's no guarantee that Z is also equal. So if you're talking about a line in 3 dimensions, you could have the X and the Y in the same spot, but if your Z is someplace different, it's not the same point. So finding this is useful, but we have to check it in the third to make sure it actually works. So that's where we'll move on to the next part, and we're going to verify this in 3. So verify in 3. And I'm going to put a big arrow to the next page. And in 3, so verify in 3. So for 3, the left side was 4s plus 3t. You can trust that that's what it was. I have it written on the paper now. And then the right side was 2. So I plug in those two values that I just solved for s was -1 and plus 3 is 2. So -4 plus 6 is 2. Left side does equal right side, and it does verify. So that means that these s and t have guaranteed that not only did I find the matching x and the matching y, but I also found the matching z. Now I actually got to figure out what that point is. So I can now take either s or t and sub it into the first or second. Of course, the s would go in the first, the t would go into the second to find your corresponding answer. I think I'm going to take the t and sub it into the second one because my notes that I'll share afterwards, I subbed s into the first, but I want proof here that didn't matter which one you did. So I'm now going to sub t. T was 2 into L2. And that'll get me each of the coordinates. So x is going to be -t. So that's -2, which is obviously -2. Y is 2 times t minus 9. So 2 times 2 minus 9 is 4 minus 9 is -5. And z is -1 minus 3t. So -1 minus 3 times 2, -1 minus 6, -7. And therefore, the point is -2, -5, -7. And regardless of which direction vectors you used at the beginning, if you use scalar multiples of them, or if you use different equations to solve it, you will always get this. If they exist, you will get the same answer. So if you got an answer that's different than this, like say you got 2, 5, 7, that's wrong. Okay, it's not scalar multiples of points. Points could only be one answer. Okay, so everyone, regardless of the method you use, should end up with -2, -5, -7. Oh crap, I did all that on a page that you couldn't see. Sorry about that. Were you able to follow along?
No, I was watching in the Meet, so I'm good.
Okay.
In the
All right.
in the Jamboard, sorry.
Yeah, on the Jamboard. Okay, good. Sorry about that. Forgot to move my page. I moved it on my iPad, but so there's the verification, there's the substitution, and there's our point. Okay. Questions?